Welcome to homework.
So here we have, and again you can see the figure in the book, we have this kind of cage structure here that's pinned up here, and it's big enough for a vehicle to be put in it, and then we can swing about this as a pendulum about this point here. And so we're given a lot of information about it. We're told that it weighs 400 kilograms initially, and it has a center of mass that is, let's see here, is 2.5 meters below the pivot point. And it has a natural period of oscillation of 2.38 seconds. So this is with no vehicle in it. Now, we put a vehicle in it, and the vehicle has a mass of 1,200 kilograms. We now measure the period to be 3.16 seconds. And let's see here, we have the distance. This is the distance from the pivot to the center of mass of the vehicle. Yeah, so this is from the pivot to the center of mass of the vehicle. Now, we can just do our simple pendulum equations to figure out that, let's see here. Initially, we have just this thing swinging, so we have J naught theta double dot plus mgd theta equals 0. Okay, so doing free body diagrams, we'll get all that. Which means that the period is, let's see here, the period is 2 pi square root of J naught all over mgd. Okay, and so in the first case, we are given T1, and then I call J naught 1. This is the moment of inertia of the platform, or of the cage, and then the mass of the cage, and then the distance from the pivot to the center of mass of the cage. And that will give us J01, which is, this is the mass moment of inertia of this this support structure about the pivot point, and that's 1,410 kilogram meter squared. Now, we need to figure out where the center of mass of the support structure and the car is. So that is defined as the total mass times the center of mass of the system equals the sum of the mass times the center of mass, the length of the center of mass of each component. So the structure had is M1D1, and then plus the vehicle was M2L. This gives us that D is almost exactly 2 meters. So the pendulum length, the center of mass has moved up as we'd expect, and now the length of the pendulum arm is now to the center of mass from the pivot point is now 2 meters. So now we have, again, we can use our pendulum equation, but now we have our total mass moment of inertia and our total mass and our new D. And plugging in everything, we get that the period is 2 pi times the mass moment of inertia of each object, then divided by the total mass times G times the distance from the pivot to the new center of mass. That then gives us that, let's see here, I think I forgot to write in what this was. This is J naught 2, I think. Let me check. Might be the sum of the two things. Might be not that anywhere. Let me check what this is. Problem 28. Why did I not write that down? This seems like it is probably, yeah, I think it is J naught 2. I think that's what this is. I think it is J naught 2. And not this total. Might be the total. Anyway, the answer is, I can't remember what this is, but if we get the mass moment, well, regardless of what it is, we can figure out what J naught 0 is. Even if it's the sum of these two, then we need to take that away from it to get J naught 2. So we get this, and then we know from the parallel axis theorem that J naught 2 equals JCM plus M2L squared, where L is the distance from the pivot to the center of mass of the object we're interested in. And that we were given. So we can then calculate the moment of inertia about the center of mass of the vehicle. And it turns out to be about 2,500 kilogram meter squared. So I guess this is a good way, a way of measuring the mass moment of inertia about the center of a vehicle, or really the center of any object.